Deep learning has entered the low-bit era. With specialized hardware and algorithmic advances, quantization, reducing the numerical precision of neural networks, has become the backbone of efficient large language model deployment. Modern LLMs, trained in mixed 16 and 32-bit formats across trillions of tokens, can now be compressed post-training into 4-bit, even 3-bit representations. This process, known as post-training quantization, unlocks massive gains in inference speed and memory efficiency, enabling everything from on-device AI to scalable cloud services. But here's the paradox. Despite widespread adoption, we still don't fully understand why some models quantize cleanly while others degrade sharply under the same compression. Recent studies suggest that as models train on more data, scaling up to 100 trillion tokens, quantization performance deteriorates. The narrative has been, more data right arrow worse quantization. And so the assumption grew that future models, trained on ever larger datasets, might become inherently brittle to quantization. But what if that assumption is wrong? Our research reveals a deeper truth. Quantization robustness isn't driven primarily by data scale, but by training dynamics. Specifically, the way the learning rate evolves during training, its schedule, plays a far more decisive role than previously thought. Let's walk through the evidence. We analyzed quantization error across the full training trajectories of 6 major open-source LLMs, ranging from 1B to 32B parameters, trained on up to 15 trillion tokens. We used GPTQ, a leading quantization method, to evaluate 3-bit and 4-bit performance at hundreds of intermediate checkpoints. What we found was striking. In every model, quantization error remains stable during the constant learning rate phase, even as validation loss continues to improve. But once the learning rate begins to decay, typically in the final 10% of training, quantization error spikes dramatically. This happens regardless of how much data the model has seen. Take small LM3, trained on 11 trillion tokens. During the stable phase, quantization error holds steady. But as the learning rate decays, error surges by orders of magnitude. The same pattern repeats in OpenSci1, 3B, Apertus 8B, and the full Almo 2 suite. Even in models with vastly different data scales, the spike aligns perfectly with the learning rate decay. This suggests a critical insight. The degradation isn't caused by overfitting or data complexity. It's caused by the optimization dynamics themselves. To isolate this effect, we conducted controlled experiments. We trained a 160M parameter transformer up to 100 billion tokens using a warm-up, stable, decay, WSD, schedule, decaying the learning rate at different points. 12B, 28B, 46B, 64B, 82B tokens. Despite varying training durations, all models showed nearly identical quantization error after decay. The spike wasn't tied to token count, it was tied to the act of learning rate decay. Now, compare this to prior work that attributed quantization degradation to dataset size. In one widely cited study, researchers observed that models trained on more data had higher PTQ error. But they didn't control for learning rate schedules. When we replicate their analysis using a WSD schedule instead of cosine decay, the trend vanishes, or even reverses. In fact, under WSD, quantization error grows slower with training duration. At 160M parameters, it stabilizes. At 70M, it barely increases. So why the contradiction? Because learning rate schedule is a confounding variable. It's not data volume, it's how you train that determines quantization robustness. But here's the real breakthrough: we can fix this. Our experiments show that larger peak learning rates lead to significantly lower quantization error, without sacrificing full precision performance. In one run, a model trained with a 3E3 learning rate achieved the same validation loss as one trained with 1E3, but its 3-bit quantized version was dramatically more accurate. This means, when choosing between two hyperparameter configurations that yield similar model performance, choose the higher learning rate. It's not just better for convergence, it's better for deployability. Even more promising, weight averaging, a simple, off-the-shelf technique, can mimic the benefits of learning rate decay while improving quantization robustness. We trained a model with a constant learning rate, then averaged its weights across checkpoints using latest weight averaging, LAWA. In the full precision setting, LAWA fell short of models with decay. But in 3-bit quantization, it outperformed all cooldowns. The averaged model was more robust, more stable, and less sensitive to quantization noise. This effect wasn't limited to synthetic experiments. When we applied LAWA to real open-source models, Almo 1B, Almo 2-1B, Almo 2-7B, we saw consistent improvements. Even when averaging across different data mixtures, what's known as model souping, the resulting ensembles showed lower quantization error than any individual model. So why does averaging help? Intuitively, it smooths out the noise in the training trajectory. It acts like a low-pass filter on the model's weights, reducing high-frequency fluctuations that become amplified during quantization. And crucially, it allows us to maintain higher learning rates longer, avoiding the dangerous decay phase altogether. We also tested other factors: gradient norms, optimizer choice, and weight decay. We found that while larger weight decay correlates with better quantization robustness, especially when full precision loss is held constant, it has a smaller effect than learning rate. And the gradient norm, though it spikes at the end of training, doesn't directly drive quantization error. So the relationship is more complex than simple sensitivity to gradients. What does all this mean? It means the narrative of more data right arrow worse quantization is incomplete. It's not scale that breaks quantization, it's how you train. And here's the takeaway. Quantization robustness should be a core metric in hyperparameter tuning. When designing training runs, engineers should monitor quantization error throughout the training trajectory, not just at the end. A model that converges smoothly with a high learning rate may be far more deployable than one that decays slowly, even if both achieve the same validation loss. This isn't just theoretical. The implications are practical. For model providers, this means you can train larger models on more data without sacrificing low-bit performance, by simply choosing better training dynamics. For hobbyists and developers, it means you can get better quantized models with fewer resources, by tweaking learning rate schedules and applying averaging. In short, quantization degradation isn't an inevitable cost of scale. It's a design choice. And now we have the tools to make better ones. So the next time you train a model, ask not just how well does it perform, but how well can it be quantized? Because in the era of low-bit inference, robustness isn't a bonus, it's a necessity. And the key to it? Not more data, not bigger models, but smarter training dynamics.